Hey everybody, welcome back. This is Divide and Conquer for the live performance exercises of Module 3, and it's actually the last problem in this section of the prep course, so congratulations on making it this far, and take a breather, just because the problem that we're about to do is slightly different than the rest of the problems we've done previously. In fact, this one is going to introduce a computer science concept. They're calling it Divide and Conquer. You can also think of it as binary search. Essentially, this is one of the first times in the course where we're going to start paying attention to, rather than just making sure that your code does what it ought to, that it does so efficiently, and that there's also a way where we can not necessarily guarantee, but more or less guarantee that a piece of code or an algorithm is going to run faster than another approach. So let's start with what we would do ordinarily. We're going to structure this problem the exact same way as we ordinarily would, but right in the middle we're going to take a rather significant detour and go chat about it and walk through a demonstration on what's going on here. So binary search is a let's do what we've been doing. Go to Replit, scroll down to the bottom and select JavaScript. Then we're going to change it to dark mode because that's how we roll. Please see a previous video for some nonsense about aperture or background of surfaces being dark versus light. There's some reason why it's not just an affectation to change it to dark mode. Anyway, that is not what we're looking for. That's the obfuscated code. So let's go ahead and grab the deobfuscated code, which is to say the deobfuscated instructions. And okay, binary search is a technique for rapidly searching a sorted collection by cutting the search space in half at every pass. So given a sorted array such as this, 1, 3, 16, 22, 31, 33, 34, you can search for the value of 31 as follows. Pick the midpoint of 22. If the value is higher than 22, so now consider only the right half of the previous array, basically this part. Pick the midpoint of that, 33. The value is lower than 33. Remember, we're looking for the value 31, so consider the left half of that, which is just basically this one. Pick the midpoint, it's 31. That is our value, so we're going to return the index of that value, which, we would return the index of that value. Essentially, that's how we're going to do this. Sorry, that was a rather awkward pause, but we'll be able to get the index for this, and it won't be that difficult because it's just not going to be that difficult because arrays are nicely ordered like that. There's a version of this that uses recursion. Now, if you don't know what recursion is, don't really worry about it, but it is kind of coming up rapidly, so you might want to start familiarizing yourself with what recursion is. And a challenge for anybody who has done this problem and kind of well on their way towards the immersive is to solve this problem using a recursive solution. There's one tiny little wrinkle, and the wrinkle happens to be returning the index. Finding whether it's present or not is not that difficult for a recursive solution, but making sure that you keep track of the index does require you to do a little bit of extra wrinkling. So return the index of the value. Notes, if you don't find the value, you can return null. Okay. If at any point you calculate the index of the midpoint and get a fractional number, just round it down or floor it, which sounds good. So there's no real context clues in terms of what the name of this function should be called. So let's call it function binary search. Binary search is going to take in an array, and it's going to take in a target, and it's going to do some stuff. Now, if we look at the return value of this, it's either going to be null or it's going to be some index, 0 through whatever the length of the array is, -1. Yep. So if that's the case, we're going to write an assertion function, which will be assert equal. Assert equal is going to take an actual, and expected, and a test name. And yeah, let's do this one. If actual is strictly equal to expected, we want a console.log passed. We're going to use the ES6. Well, I hope it's ES6. We're going to use the relatively new feature in JavaScript, and relatively is exactly the way to say that because it was new when I was first coming up, which was a while ago. So these template literals, which will allow us to directly interpolate a value into the string. So failed test name and expected. We'll interpolate our expected value. And we've got to put quotes here. We've got to delete the second one because That's how they do. Expected that, but got, and then our actual value. Quotes, delete the second one, and put a semicolon just to make everybody happy. Okay, so first will be actual found, because this will refer to one where we found what we were looking for. We'll say binary search. We're going to pass in this array from the example, just because, why not? And the target that we're looking for is 31. Slide this over just a bit so my semicolon can fit. Say variable expected found. You don't actually need to declare a variable for these. You can usually just kind of put the value directly into your call to assert equal, but I like to do expected found. An expected found is going to be 0, 1, 2, 3, 4, so it should be 4. We'll make our call to assert equal with actual found, expected found, and should return index of value when value is present. Go ahead and copy all of this. We'll say actual not found, and then expected not found, and we ran out of room for our semicolon again, so I'm going to move it over. You don't need to do that. It's not going to change a single thing. In fact, as you'll notice, it doesn't even really define this as a separate line. It just displays it that way. It considers all of this to be on line 41, but I really like things to look nice, so I'm going to move that over. So for binary search for a value that's not found, let's have one that's kind of in between here. So we'll say something like 9. 9 is not going to be found, so the return value should be null based on the instructions. Copy and paste both of these in, and say should return null. Turn null when value is not present. Okay, so now that we have two test cases, one for the affirmative, one for the affirmative, negative. Anyway, we have two test cases, and that's going to be sufficient for our purposes. Let's go ahead and hit run, which is going to confirm that our assert equal function is written correctly, and that our test cases don't have any obvious errors in them, besides the fact that binary search doesn't return anything. And we got our nice, hey, I expected this, but I got undefined for both cases, so we are in good shape for now. So at this point, there's two ways that we could go. We could start trying to put this algorithm that they wrote out for us into pseudocode inside of here, but instead what we're going to do is we're going to do something we haven't done quite yet. I'm going to open up a new tab, and in the right-hand corner here, you'll see that because I'm on my Google account, I can click on the Google Apps and go to Drive. Now, Drive is a great place to store spreadsheets, documents. Essentially, it's like a free open source version of almost all of the Microsoft Word, Microsoft Excel, Microsoft PowerPoint. All of that good stuff is kind of for free within Google, and it's shareable, very, very good tool for software engineers, and just really anybody in general. So I'm going to click on Drive because I've actually already gone in there and created a divide and conquer demo. So there's two versions of this. One is going to be the generic case. So if I'm looking to see if I have a value in here, let's consider that what's here on line 9 is an array of values. Cool. Is an array of values from, let's make sure this is nice and big, and there you go. So it's an array of values that go from 1 to 30. And the way that we're going to go ahead and approach this is first, let's consider a brute force solution to see if I have a number in this array. Now, let's consider that I'm looking for the number 22. And let's assume that I'm not aware that this is just a sequential series of numbers. The sequential series of numbers is much more for demonstrative purposes than it is to, for any other purpose. So if I'm looking for 22, what I could do is just start at the very beginning and say, is this 22? And if it's not, just keep going. It might seem like a bit of a stretch, but the problem with this is that my search time, or the number of steps that I have to take to get to my answer, is going to be possibly dependent on the length of the input. This is something called, there's so many ways to describe this, and I don't want to get into too much detail for two reasons. One is that it's not of immense importance at the moment, and two is that I haven't really lectured about this before, so it's possible that I will say some things that are not necessarily 100% correct or could be confusing. And so the way we want to think about this is that the fewer steps that we can take to check to see if our number is present is going to be a direction we're going to want to head in. If we check every number sequentially, it's possible, let's say that we're looking for the number 51. If we're looking for the number 51, we were going to make 30 checks before we have to say, okay, 51 is not there. And we call that O of n. Essentially, that means in the worst case, it's possible that I would have to look at n, meaning the number of elements in the input, to find if an element is there or not. And while that's okay, it's not ideal, and what we're about to find out is that we can make it better. So if we look at the instructions for what they told us to do, they said pick the midpoint. So it's like, okay, I'll pick the midpoint. Midpoint is 15. Now if I check back with my instructions, the value is higher than 22. And if we look, 51, is 51 higher or less than 15? And the idea for that is that it's, well, it's higher. So what that means is that this entire section now, including 15, can be considered superfluous, which is to say that I don't need to check 2, 3, 4, 1, 8, any of these, because if I checked 15 and the number's higher than that, and I know that the array is ordered, I can immediately cross off half of the work that I would have to do. So now, even if I linearly searched, which is to say searched sequentially one by one the rest of the array, I've already cut in half the number of guesses I would have to make. But we don't need to stop there. We can do the exact same thing. So if we go to the midpoint of this, it's going to be somewhere around, oh boy, 1, 2, 3, 4, somewhere around here. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we're in good shape on that one as well. And so if I pick 23 and I look, okay, is 23, and I'm looking for 51, 23 is less than 51. So I can again cross off basically the entire left side of the remaining searchable array and just search for it in this one. Now, if you're keeping track, we made one guess here and cut off half of it, so we're at 1. We made a second guess and now cut off the remaining half there, so we've made 2 guesses. If we keep going, 27 and cut off this half, that's 3 guesses. And if I look for here, I go for 29, that's going to be too low, so I cut off all of this. And that was 4. And now I make my 5th guess, 30. It's not. I'm at the end of the array, or I'm at the end of the searchable portion, and I've made 5 guesses. So instead of having to make 30 possible guesses, I made 5. Now, you're going to have to make a leap with me here. Essentially what we've done is we've taken a logarithm, or we have taken an inverse of an exponent, number of guesses. Oh man, see, I'm butchering this. Essentially what we want to consider is that we are reducing by a very significant order of magnitude the number of guesses that we would have to make by adopting this algorithm. So let's jump to a specific example and possibly just forget about all of that. But for the most part, the idea is that we are, instead of just searching one by one, we are using the fact that the array is ordered to select the midpoint, check to see if it is greater or less than the number we're looking for, and then remove from the searchable area that we're considering whatever the other side is. So if the number is less than 15, we would cut off all of this. And if the number is greater than, as it was previously, we would cut off all of this. The transfer from this to an actual algorithm is going to be a little bit easier if we consider a specific example. So let's go ahead and consider this one. This is the actual array that they gave us. So let's look at the instructions again. Pick the midpoint, 22. So I'm going to pick the midpoint. I'm going to say midpoint here. Now if I go back, I say the value is higher than 22 because I'm looking for 31. So that means I can remove from consideration this. So I'm going to highlight it red to indicate that it is no longer part of what I'm searching for. The next thing they want us to do is to pick the midpoint again of the remaining thing. So this will be our first level, and this will be our second step. So now I'm going to put a midpoint here, and we're looking for 31, which means that it's less than our midpoint. So we remove from consideration the midpoint that was incorrect and everything above it. Now for our third guess, we're going to guess the midpoint of the remaining section, which is essentially just 31. We pick the midpoint. It is our number, and so we're going to return this index, which is 0, 1, 2, 3, 4. So we'll return 4 at that point. So what we're about to do is one of those moments where it's like, how did he guess that? I did not. I am not a cook. I'm sorry, I'm not a chef when it comes to this stuff, but I am a cook. And so what I did was look up a recipe where somebody solved this, and the recipe calls for what I'm about to do. So the way that we are going to define the portion that we're still looking at is that we're going to define a min and we're going to define a max. At this point, the minimum value for the number that we're searching for could be here, and the maximum value could be here. We don't really care about any indexes that are beyond this or below this because they're not really defined. Then we're going to take the midpoint of the min and max, select that, and then proceed from there. So we have a midpoint, and this is our first pass. Now what we did previously was we were looking for 31, so we checked the midpoint. The midpoint is less than 31, so we're going to remove all of this from consideration, which we're going to do by highlighting again in red. But let's think about what that actually means. On step 2, what we need to do is check to make sure, we need to redefine the min and max. So what we'll do is we'll define min to essentially be the midpoint plus 1, or 1 more than the midpoint's previous value. So we'll say the min is now here. The max doesn't change because we had a situation where we're only adjusting the min, where we're saying this is no longer part of the category I want to search for, so the minimum index that I would care about is now here. Same thing that we're going to do over again. We're going to check the midpoint. Now for this one, let's go ahead and consider that our value that we're looking for is, rather than 31, let's say it's 30, because this is going to help us define when we should stop doing, running our algorithm. So we have the midpoint, we check 33. Again, we're looking for 30 this time. So if we're looking for 30, we check the midpoint. The midpoint is greater than 30, so we need to get rid of the right side of the array. Right side of the remaining searchable portion, that is. So now, on our third step, this is where things are going to get a little bit odd in this demonstration, but we have the min is here, the max is here. They're both for 31. And then we're going to check the midpoint. So the midpoint is 31, so we'll say midpoint as well. 31 is not the value that we're looking for. So here's where things are going to start to get a little bit odd. Let's actually take away the midpoint guess here and put it there. And essentially what happens here is that because the value that I'm looking for is 30, we want to follow the exact same pattern. We cross off the midpoint and anything to the right of it, which is just the midpoint itself, and then we move the maximum value to be 1 less than our previous midpoint. So now our max is here and our min is here. And this is what we're going to call a stop condition. Because the max is no longer equal to or greater than our minimum, we can define the situation thus. We have searched everything that we need to, and we should stop and return null. If all of that was confusing, it's probably because it wasn't that good of a walkthrough, but it's an amateur walkthrough, and at this point, I feel like that's probably going to be a good step for y'all. So let's go ahead and head back to Replit and see if we can organize our thinking around what we just did. So the first thing that we do is we pick the midpoint. So we'll need a variable midpoint. The second thing that we're going to need is a max and a min. So we'll say variable min is equal to 0 because that's the beginning of the array. We'll say variable max is equal to the last available index in the array, which is going to be array length minus 1. And then what we want to do is essentially check to see if the midpoint is, or get a value for the midpoint. Now, there's a bunch of ways to do this, but one relatively convenient way is to take the average of the min and the max and then floor that value. So we'll say midpoint, and we don't really need to define this separately, so let's just call it variable midpoint. And we're going to set that equal to math.floor max plus min divided by 2. And in case you are not sure if that's going to work, you can kind of work it out with one of these. So I'm going to copy this, we're going to move it down a little bit, and I'm going to show you what I mean by basically what I just said. So we'll get this as a white background, we'll put some indexes in here. So if I want the midpoint to be 3, 0 plus 6 divided by 2 is going to give us 3. The next midpoint, let's say that we crossed off this portion of it. If I want the midpoint between 3 and 6, 3 plus 6 is 9, divided by 2 is 4.5, and if we floor that, we're going to get 4. So that's a relatively convenient midpoint for us. Now, we actually did it slightly differently on this one, but that's not that big of a deal. You want to picture that. Oh, no, I did that incorrectly. My sincere apologies. So if we move min to be the index 4, 4 plus 6 is 10, divided by 2 is going to be 5. So that's going to give us our midpoint here. So that's going to be the operation we do to regularly update our midpoint, and so that's why we've written it as such. Now, if we remember what was going on here with the max and the min, that's how we're going to define these operations. They're going to happen while the min and the max are values that make sense, meaning min is less than or equal to max. So if we come back here, we want to say while min is less than or equal to max. Also, a quick update, I've never done this in this fashion before, and so I'm kind of operating half off memory. If we do this incorrectly, we'll fix it, but it might be the case that we're doing something incorrectly, and so if we are, just bear with us. While min is less than max, we're going to check to see if target is equal to array at midpoint. If that's the case, we're going to return midpoint. Because if you think about it, midpoint is the index. So if we find that the array's value at that midpoint index is equal to the target, that's the value that we actually want from our binary search. Now, what we need to do here is kind of organize the way we think about it based on where the target is compared to the value at the array's midpoint. So we're guessing at the midpoint, and we want to have two considerations. One would be if the target value is less than the value at the midpoint. And let's think about what that would be. If the target value is less than the value at the midpoint, then that means that basically the midpoint and everything above it doesn't matter for us anymore. So we're going to reset max to be midpoint minus 1. And let's kind of jump back over here and consider how that would work. Let's say that we pick our min and our max here, and max, and that's going to bug me. So if min and max, and what we're saying is that this is the case where we pick the midpoint, and the midpoint, the target value is less than the value at the midpoint, meaning that we're looking for something like 3 or 16. So we pick the midpoint, we have a value of 22, and we say, okay, so the value that we're looking for is less than that, so we need to get rid of this part. Now we get rid of this part by reassigning max to be the midpoint minus 1, which means that max would now be here, and min wouldn't change. So that's one version. So let's go ahead and write that out. Say if target is less than the value at the array midpoint, then we'll reset max to be, oh boy, there we go. Say max is equal to midpoint minus 1. Now if we consider the opposite case, let's write the pseudocode first. Say if the target value is greater than the value at the midpoint, we want to reset min to be the midpoint plus 1. Now this might be obvious based on the demonstration we just did, but let's go ahead and do it again. So let's say we're looking for a value 31, which we were originally. We pick the midpoint here. 31 is greater than the value at the midpoint. So if that's the case, we want to get rid of all of this part as an applicable searchable, as an applicable portion of the array that we should continue to search, and we do that by reassigning min to be the midpoint plus 1. So min gets set here, max gets set there. Sorry, max does not get affected. So if that is the case, we're going to say if target is greater than the array value at the midpoint. You'll also see some people write this where instead of saying midpoint, they'll say guess, but that's okay. Min is going to be equal to the midpoint plus 1. So let's consider from a global view what's happening here. We're reassigning the min and the max based on the targets either being less than or greater than the value at the midpoint that we're selecting. But the other thing that we're going to need to do is we need to reset the midpoint. So if we don't do anything else, the midpoint's not going to change, and it's going to just continually check to see, hey, is the first value that I chose in that middle of the array the value yet? Now, since it's not, we're going to get this weird situation where it just doesn't do what it ought to. So at this point, we're going to need to guess or reset the midpoint to be middle of remaining array. And if we consider what's happening there, the midpoint of the remaining array is that same operation that we did originally. That same operation where we say midpoint is equal to math.floor of max and min divided by 2. So we're essentially just going to copy this portion from the original declaration, come down here and paste that. So this is going to allow us to, in the event that we didn't get the value, we either reassign max or min to reduce the amount of searchable array that we have left, and then we reselect a midpoint. When this happens, we're going to continue to check to make sure that the min is less than or equal to the max. If it is, return the midpoint. And at a certain point, we'll get to an area where the max is set to a value below min, or min is set to a value above max. And at that point, the while loop is going to complete, which means that if the while loop is still running, we have a possibility of finding our midpoint, or finding the index where our value is. The issue that we come across is that if the while loop stops, we know the target value is not present. Which means, quite simply, return null. If the while loop stops, then this code is going to run, which means that at this point we know we have not found the value that we're looking for, so we can return null. A lot of information in this video. It is not exactly as curated or as perfect as we would like, but you want to figure that sometimes it helps to see somebody struggle through these things, and so that's why we're kind of doing it a little bit more piecemeal. Might put another video in here that's going to be a little bit more directed and straightforward. If you want a tutorial of this, I cannot recommend Khan Academy's computer science class enough. It's actually mentioned in some of the later modules, which are maybe broken off into their own course, but one of the things that they reference is the Khan Academy computer science course. It's taught in JavaScript. They actually go over this in detail. It's a very, very useful course. I cannot recommend it enough. So I think that this problem is going to work. Let's make sure that, okay, max is getting set to midpoint -1, min is getting set to midpoint +1, and that's in the case where the target is greater than the value we've selected. And we're reassigning the midpoint each time. So I think that this should be everything that we need. In the event that this is a while loop, that this is an infinite loop I've created, you'll probably never see this video, but in the event that we get past, we can reasonably assume that we've done everything correctly. So I'll leave all of the code kind of in the window. We'll hit run, fingers crossed, and we did it. So let's go ahead and copy all of this, come back to our divide and conquer area. Again, this is sort of just a superfluous victory lap because there are no tests here. The test that we wrote and any additional tests that you wrote are also kind of part of what we're up to here. So there it is in all of its glory, I suppose. Let's go ahead and hit run tests. And we're in good shape. So thanks for watching this video. I hope you enjoyed it, and we'll see you in the next one.